morning. Welcome you to this session. In the last session, we started the discussion on availability or exergy or available energy, and we just recapitulate again what we discussed in the last section, that with respect to heat, the energy in transit from a temperature T1, just a recapitulation, if heat Q is available from a temperature T1, then the maximum work which is possible with reference to a fixed environment temperature T0 was ascribed to its availability or available energy of Q. So, we can write the availability. These are the synonymous terminology as we told in the last class. Availability of Q derived from I am writing derived from a temperature T1 with respect to a reference environment temperature. Why I am writing this thing? Because these are the specification. That means the availability or available energy of some heat quantity depends upon the temperature at which it is obtained, from which it is obtained, and the reference environment temperature. Sometimes it is referred to as exergy or availability reference environment temperature. So, this becomes equal to the work by a Carnot cycle, that means Q into 1 minus T0 by T1. Well, at the same time we also appreciated that if this same heat, instead of obtaining from T1, could have been obtained from another temperature T2 which is less than T1, which means that if we first transfer this heat from a high temperature pot or reservoir to a low temperature, relatively low temperature reservoir T2, and then derive this Q from a low temperature, then this availability of Q with reference to the same availability reference temperature, that is T0 environment temperature, availability of Q from T2 will be what? Will be equal to Q into 1 minus T0 by T2. And since T2 is less than T1, obviously the availability from T2 is less than this. Let us consider this as A1 and this as A2. Since T2 is less than T1, A2 is less than A1. What is this difference then? You just calculate. A2 is less than A1. So, what is A1 minus A2? E2 will be Q into 1 by T2 minus 1 by T1. So, this much is the loss difference in the available energy. That means the available energy or availability of Q is reduced when it is obtainable from a temperature T2 rather than temperature T1, where T2 is less than T1, by this amount. Now, what exactly? Yes, any question? Into T naught, very correct, into T naught, very correct. So, now what exactly this amounts to be? We should know what exactly this means, that difference in available energy which is lost. This available energy is lost when you transfer the heat from high temperature to low temperature. To understand this thing, let us go through the concept of irreversibility. What is meant by irreversibility? Very good. Irreversibility. Irreversibility in a process. As you know, all natural process is an irreversible process. All natural process is an irreversible process. So, what is the criterion of irreversibility? We know from the entropy principle that when a system interacts with its surrounding and performs a process which may be an ideal or natural, the basic principle from second law as far as the change of entropy of the system and the surrounding is concerned is that algebraic sum of the entropy change of the system and surrounding, which is known as the entropy change of the universe, which is entropy change of the system plus entropy change of the surrounding, will be greater than equals to 0 when the process is reversible for both the system and the surrounding, which means the entire process, if you consider the system and the surrounding as an equivalent isolated system, which is termed as in a limited sense as the universe is totally reversible, then the entropy change of the system plus the entropy change of the surrounding becomes 0. That means they become exactly equal but in opposite in magnitude. Okay. Otherwise, this algebraic sum of these entropy changes, which is entropy change of the universe, is greater than 0. Therefore, entropy change of the universe is definitely a criterion for the reversibility of a process. If a process is both externally and internally reversible, you understand, then this entropy change becomes 0. So, if the change in entropy change of the universe approaching 0 as the process performed by this system approaches a reversible process. So, therefore, you see delta S system plus delta S surrounding is equal to delta S universe, and delta S universe according to second law of thermodynamics is equal to 0. For a natural process greater than 0, for an ideal process equals to 0. Now, this equation can be interpreted in various forms. I just write now, this delta S universe sometimes can be written as generation of entropy or production, generation or production of entropy. Very simple, production of entropy. It is very simple. If you consider a system, it is a very simple, and if you consider a surrounding, it is a primary school level mathematics, surroundings, and if you designate the system entropy initially S1 and final S2, and the surrounding entropy initially S01 and final S02, then delta S system is S2 minus S1 and delta S universe is S02 minus S01. That becomes equal to surrounding, I am sorry, is equal to delta S universe, which becomes equal to, that means if you see that delta S2 plus delta S2 plus SO2 minus S1 plus SO1. So, therefore, you see this delta S universe represents the sum of the entropy after the process minus the sum of the entropy before the process. That if you designate some entropy, some absolute entropy of the system S1 at the beginning of the process and that of the surrounding. When the process takes place, only we equate the entropy change. So, therefore, we designate a final entropy S2 so that the change is S2 minus S1. Similarly, the surrounding suffers a change in entropy so that its final entropy becomes SO2 or S02 as you call. So, this is the change of entropy of the surrounding. That means, this change of entropy of the system plus surrounding is the change of entropy of the universe is nothing but the change of the entropy of the total isolated equivalent isolated system or universe. That means, initial entropy of the system, that means final entropy of the system minus initial entropy of the system, and that is always greater than 0, means in all natural processes entropy is generated, because this is more than this. If the process is an ideal one, that is reversible interactions, then the entropy before and after remains the same. Otherwise, always entropy generated is generated. That means entropy of the universe, that means this is universe, is always generated. Universe, that means the entropy of the universe is monotonically increasing for all natural interactions within the universe. So, that is why it is sometimes written as entropy generation. Now, if you write in this way, then we write delta S system plus delta S surroundings. You must know the various forms so that you should not have any confusion, can be written as entropy generated. Delta S universe I write now the generation of entropy or entropy generated, generation of entropy, generation of entropy, generation of entropy, the production or generation of entropy. Now, in irreversible thermodynamics, sometimes this delta S surrounding is written as delta S system is all right, change of, what is delta S system? Now, I write in language change of entropy of a system. Now, this delta S surrounding is sometimes written as net, is a concept of entropy flow, net entropy flow or entropy transferred out, flowing out, net entropy outflow or entropy transferred out from the system. In case of a closed system, we usually use this terminology, entropy transferred out or entropy outflow, whatever. So, therefore, this plus this is equal to generation of entropy. Generation, this is the language which is used sometimes in irreversible thermodynamics. Now, how you equate delta S surroundings? Just you see that there is a system, there is a surrounding at T0. Let the system is heated by an amount Q. The entropy changes from S1 to S2. So, according to our classical reversible thermodynamics, this statement is that delta S system S2 minus S1 plus delta S surrounding. What is delta S surrounding? It is a reservoir at constant temperature. Heat is being rejected. That means this will be minus Q by T0. And this part is the same, entropy generation, delta S universe, which is nothing but entropy generation or production. So, you see this minus Q by T0 can be looked as the net entropy transferred out or entropy flow out of the system with a minus sign, because it is coming in. So, minus of that is going out. If the system could have rejected the heat Q to the surrounding, then surrounding entropy could have increased. So, it could have been plus Q by T0. That means this is entropy outflow or entropy transferred out. So, this is nothing but the entropy outflow or entropy transferred out from the system. This is synonymous to the delta S surrounding. That means whether I write in this version or write in this version, change of entropy of the system plus change of entropy of the surrounding is the same thing, and whether I write delta S universe or entropy generation rate is the same thing. Again you see another equation which you already appreciated, that delta S of a system, you please be careful, I can tell you not in a single book this is so elaborately explained, these three equations for the entropy change and the relationship between these three. They are the same equation, synonymous equation, but explained or interpreted in different way. Now, plus we know that thing delta Q by T is equal to internal irreversibility. That means it is the entropy change due to internal irreversibility. We appreciated that delta Q by T, delta S system. What is this delta Q by T? This is an integral evaluated with the system temperature. But if I just substitute this or write this delta S system, this we discussed earlier, plus delta Q by T0, where T0 is the surrounding temperature, this is little changed as delta Si plus delta So. I write is that delta S, where I tell that delta S is the entropy change due to both internal and external irreversibilities, where I consider this as the surrounding temperature. So therefore, you see this is delta S system and this is an integral delta Q by T0, where T0 is the surrounding temperature. If you think it of this T as the system temperature, then it is the entropy change due to internal irreversibility. This is the entropy change due to external irreversibilities plus internal irreversibility. This is the entropy change because of the heat transfer to the system. If you evaluate this at surrounding temperature, then you will see this is nothing but equivalent to this net entropy outflow transferred out, and this is the delta S surrounding. Okay, so therefore, you see the delta S system, oh sorry, I am extremely sorry, this will be minus, I am extremely sorry. So, this will be nothing but the entropy change of the surrounding, this will be this side, delta S system is delta Qt plus delta Si, I am sorry, so there will be a minus sign. Therefore, we see now what I want to say, that these three equations are synonymous. And this one. Now, I write this thing, these three equations, I write this thing again, which is very important for you to know at this moment. That means, I write first is that delta S system, change of entropy, delta S system, okay, plus delta S surroundings, delta S system plus delta S surrounding is delta S universe. I can write delta S system, this is nothing plus net entropy outflow or transferred out. I am not writing both these statements from this system. When I write this, usually I write generation of entropy. Generation of entropy. Sometimes I write delta S system minus integral del Q by T0 is equal to, which is the entropy change due to heat transfer, and therefore, this will be delta S, which is the entropy change due to irreversibility. When the process is both externally and internally irreversible, then delta S system is delta S. Delta S is 0, delta S system is del Q by T. So, therefore, these three equations, it is very important, are synonymous, which means that delta S, we should rather follow this one for our calculation. This will be simpler one, and we will always recognize delta S universe is nothing but the generation of entropy. That means this delta S universe, this generation of entropy same. That means delta S universe of the first equation is nothing but delta S of third equation, and these two equal to generation of entropy. That means because of irreversibility, there is always a generation of entropy in a equivalent isolated system. That means whenever there is an interaction between system and surroundings, between different systems, it causes the entropy of the equivalent isolated system or the universe to increase. That is the generation of entropy. Now, irreversibility I. Now, irreversibility, now you see, when the process is more and more irreversible, the generation of entropy will be more and more. Its value will be more and more positive. It is always positive for a natural process. When the entire interactions between the system and the surroundings or interacting systems tend to reversible process, then this generation of entropy tends to 0. So, irreversibility, therefore, the irreversibility in the process is gauged or characterized by this entropy generation, and it is quantified as some reference temperature, environment reference temperature into entropy generation, entropy or delta S universe generation. Sometimes this we or T0 delta S universe. Sometimes the entropy generation is symbolized as sigma T0 delta S. That means sigma is entropy generation, which is nothing but delta S universe. It is always better, this will be more simple to calculate system and surrounding entropy change separately, sum it up algebraically, get delta S universe, multiply it with T0 and get the value of irreversibility. So, this gives a quantified equation or quantified statement of irreversibility, which comes in terms of the energy, because irreversibility is something due to which the energy is being converted from the higher to lower grade. So, its unit is always expressed in terms of energy. Delta S is energy per temperature, del Q by T. So, therefore, you multiply with a reference temperature, which is usually the standard environment temperature, you get the irreversibility. So, define irreversibility quantitatively for any interacting system and surrounding equivalent isolated system where a process is being taken place. You have to define the reference environment temperature based on which you define the irreversibility. All right,
so,
please.
So, why we multiplied entropy generation with T naught and not the system temperature?
Not the system temperature, it is T naught, because T naught is the reference fixed constant temperature, not by the system temperature, then irreversibility will change. So, this is a just formula. That means we take a reference value with which, that means irreversibility is directly proportional to delta S universe or entropy generation rate. T0 acts as a scale factor, a constant scale factor to express it in terms of the energy. It is not any varying temperature of the system or any varying temperature of the surrounding with which it is interacting. It is a fixed environment reference temperature. Sometimes we tell it at free stream temperature, it is a fixed reference quantity, you understand, because it acts as a scale factor with the entropy change of the universe, which is exactly the criterion which should be even the quantitative criterion for irreversibility, but to express it in terms of the energy unit, we just multiplied it with T0. All right, a fixed reference environment temperature. Now, with this, if we go back to this, that when heat is available at T1 temperature, and now instead of that, if we transfer this to T2 temperature and the same heat is taken, now we know the availability A of Q at T1 is what? Q into 1 minus T0 by T1, and availability of Q at T2 is Q into 1 minus T0 by T2. And let this is A1 and let this is A2, and A2 is less than A1, and the difference is, what is the difference? Q into 1 by T2 minus 1 by T1 T0. What is this? Now, if you consider this heat transfer process, this is an irreversible heat transfer process, heat transfer due to a finite temperature difference. Whenever I transfer heat from a high temperature to a low temperature, this is a natural process and irreversible process, irreversible heat transfer process. So, what is the entropy change of the universe? It will be greater than 0. To find this entropy change of the universe in this heat transfer process, how to find out entropy change of the universe? The entropy change of this system plus the entropy change of this system. This rejects it, so entropy change of this system at a constant temperature. This gets the same heat, QT2. So, therefore, you see Q into 1 by T2 minus 1 by T1 is the generation of entropy or the entropy change of the universe because of finite temperature difference heat transfer. There is an irreversibility. So, irreversibility due to this finite temperature difference heat transfer will be equal to T0 into delta S universe. That means T0 into Q into 1 by T2 minus 1 by T1. So, therefore, you see this quantity is nothing but the irreversibility I because of the heat transfer due to finite temperature gradients. Now, what is the philosophy? Philosophy is like that, okay sir, when I exergy or available energy is the work potential. So, we must receive the energy, low grade energy, for example heat, now we are discussing heat, for converting into work at that state when its work potential is much more. For an example, when in a cricket team, we want such a cricketer in our squad whose work potential is much more. We do not want somebody whose work potential is less. So, therefore, state is very important, that what is his potential, so that it is most likelihood that he will deliver the good. So, therefore, similar way the heat which has to be converted into work should be derived at certain state, so that its work potential or availability should be maximum. But then you, next question said, then when you transfer it to T2, this work potential is reduced. This is because of the irreversibility in the natural process through which the heat is transferred to T2. Then why do you transfer? This concept is the underlying concept that sometimes we cannot use this low grade energy at the state where its work potential is high or maximum because of some practical reasons. So that we have to transfer the heat at the lower temperature where its work potential is reduced because of this natural process of transferring this energy. Sometimes in fuel, for example, fuel has got some energy inherent in it, chemical energy. But to obtain this chemical energy into power, when this energy reaches the work producing device, we make a combustion process. We liberate heat through burning of the fuel. Then ultimately the products of combustion at high temperature and pressure comes to the working device, which contains a high thermal energy, internal energy. So, while doing so, if you evaluate the available energy or work potential of the fuel at the beginning, that will be taught afterwards in chemical availability in the chapter that chemical thermodynamics or thermodynamics of reactive system is lost. Because of these natural processes of combustion, heat transfer, all these things combined together creates a loss in the work potential availability. But we can't help, we can't use like that. More close example of this is solar energy. Even we obtain heat from sun, we cannot obtain that heat from sun's temperature, on the temperature of the sun to develop work. So, what we have to do? We have to use a collector where we collect the heat. Even if we consider the entire amount of heat is coming to this collector without any absorption in the surround medium, but the temperature of the collector from where we utilize the heat or a medium which absorbs the heat from the collector and ultimately goes to the engine is much less than the temperature of the sun. So, if somebody equates the available energy of the amount of heat radiated from the sun at sun temperature, it is huge. But when you calculate the same amount of heat neglecting the absorption in the medium at the temperature where it is collected or absorbed by a system, available or obtainable, rather the word available I will not use here, obtainable for utilizing it in developing work through a heat engine is much less and its available energy is less. So, each and every natural process this way degrades the quality, this is known as quality of energy, that work potential of energy or available energy. I will explain this again in more detail, but now at this moment we go to another form of available energy. So far we have discussed the available energy with respect to some heat coming out at some temperature. Now you consider there is a closed system. There is a system which is at an elevated condition, that means whose state is different from the surroundings. Now there is a possibility that if this system interacts with the surrounding and come to the dead state, we can extract some work. That means this system has an work potential similar to that heat flow, similar to that of the heat energy coming from T1, and that is ascribed to as the available energy or availability of a system. Let us discuss that. Let us consider a closed system. So now I will discuss the availability. Similar way, availability, available energy, again the synonymous term available energy or exergy of a closed system, Where from the concept originates from here, that let us consider a closed system which is having a pressure P, temperature T, let volume V, let internal energy S, entropy S, internal energy U, all these things. And let the environment is at a fixed pressure and temperature P0, T0. Let P0, T0 be the pressure and temperature of the environment. Now the system is at an elevated state, that means the state point of the system is different from that of the environment. So therefore, there exists an opportunity of obtaining work from this system if it is allowed to interact with the surrounding and comes to the dead state. That means the property will be such that it will be in thermodynamic equilibrium to the surrounding. In that case, my objective is to find out what is the maximum work obtainable, and that will be defined as the availability of the closed system. All right, let us do that. Now to do it, let us consider some heat Q is given from this environment at T0. That means I cannot bring out some other system, that environment. So we have to think in terms of Q going from the environment. So it may come out from the system in that process, does not matter whether it is coming out or going in. So just by a reference, by convention, I just do it that some heat is added, and always in any general analysis we do like that, and some work is coming out of the system. And in the process where it has taken heat from the surrounding and developing work W, it has come to the dead state. That means these are the finite amount of energy interactions, after which the system comes to dead state, which means system pressure will be P0, temperature will be T0, system has to be in thermodynamic equilibrium, both mechanical and the thermal equilibrium. Here we are not considering the chemical equilibrium, no mass transfer chemical reaction is considered. That means the mechanical and thermal equilibrium will be the only criteria for the thermodynamic equilibrium. Let the corresponding properties are S0, U0, V0, like that, and let us consider this with a suffix 1, that is the initial state and that is the final state. All right, now I can write the first law of thermodynamics, Q is equal to du plus delta U plus W, and delta U is simply U0 minus U1 plus W. Now here I neglect any form of kinetic energy within the system, closed system. We consider a stationary closed system, that is why the initial internal energy is intermolecular energy. And finally, when it will be coming to a dead state, equilibrium dead state, so internal energy will be only the intermolecular energy U0. So if you consider this, then we can write this according to first law of thermodynamics. It is no problem. Now what is Q? I can write from the entropy principle that this change of entropy of this system, that is S0 minus S1, change of entropy of the surrounding minus Q by T0 has to be greater than or equal to 0. Okay, all right. Then we can write Q is less than equal to T0 S0 minus S1. So then if I substitute this inequality relation here, we can write W becomes equal to less than What is this? U1 will go this side, U1 minus U0, then plus T0 S0 minus S1. Okay, all right. Then we can write is less than U1 minus T0 S1 minus U0 minus T0 S0, the bracket. Is all right? I can write W becomes less than equals to this. Now, there is a little concept. Now, if we are interested only with the useful work, what is useful work? We are interested in form of useful work, W useful. Now, when a system delivers work, there are different form of work interactions I have told. Here generally I have written W. Now, when it delivers the displacement work, a part of it is being spent by displacing its surrounding. What is that? That means there is a system. When the system expands, for example, this is the final shape of this system. That means this difference in this volume, that means V0 is greater than V1. That means this V0 minus V1 into P0 is required to push the system. That means to this amount of work is utilized in displacing the system by an amount of V0 minus V1. So, that much work is not available as an useful work, that is being spent to the surrounding, because surrounding means that surrounding does not mean this entire environment, vast environment. That means in the immediate neighborhood of the system. That means it is another system. If two systems are in close contact, if one is expanded, consider a cylinder divided by a piston. If one side is a system, another side of the gas is the surrounding. That means when it delivers to another side of the gas, if it is allowed to maintain its pressure constant, it is being pushed. So, this V0 minus V1 into P0 is the work that is being spent by displacing the surrounding. So, this work is not the useful work. So, therefore, useful work we write W useful is equal to W minus this P0 V0 minus V1. So, therefore, I can write W useful follow is less than equal to. Now, if I subtract this, I can write this U1 plus P0 V1 minus T0 S1 minus U0 plus P0 V0 minus T0 S0. Now, you see with this expression I can write that maximum work will be equal to U1 plus P0 V1 minus T0 S1 minus U0 plus P0 V0 minus T0 S. Now, if I define a function phi like this at any state given by the P, V, T, S like this, U plus P0 V minus T0 S. Now, you see that if I define a function like this, then I can write this is the function at state 1 and this is the function at state 0. That means I can write the W maximum is this function at corresponding to state 1 corresponding to state 0. 0 is the dead state. Now, this function you see how I choose, this is not a property of the system. This does not contain only the system properties or the state variables of the system, it contains the surrounding property. That means this is a composite function of both system and surrounding variables. U is the system variable, the internal energy of the system, V is the volume of the system, S is the entropy of the system, while P0 and T0 are those of the surrounding. So, this function is a composite function. If you want to describe this as a property, then you will have to tell this is a binary property or a composite property of both system and surrounding in this fashion, U plus P0 V minus T0 S. Then this composite property evaluated at state 1 and evaluated at state 0, the difference of this is the maximum one. So, this is the, by definition, is the availability of a closed system, phi 1 minus phi 0. Okay, this phi 1 and phi 0, the phi rather, it is known as availability function, availability function. So, therefore, you see the maximum useful work obtained from a closed system which is elevated from that of the surrounding is known as availability, available energy or exergy of that closed system to that specified state with reference to a prescribed environment at P0 T0. And we know that this available energy, that is the maximum work we will get if the system is allowed to interact reversibly with this prescribed surrounding or environment and comes to the dead state, so that naturally no other process is possible. That means in that way you will get the maximum amount of work available, and that equals to the, by definition, the availability or available energy or exergy of that closed system, which equals to the difference of the two functions, availability function, difference of the same function, availability function, evaluated at state 1 and evaluated at the dead state. Now, if I tell you that what is the maximum work from a state 1 to state 2 for a closed system, not the dead state, that means a closed system at state 1 and we forcefully stop it at state 2. We make the boundary in such a way that again it comes to an equilibrium state 2 which may not be the dead state. That means the boundary is made such that no further process or interactions with the surrounding is allowed. In that case the maximum work will be phi 1 minus phi 2, very good, phi 1 minus phi 2, because phi 0 will be cancelled from both the cases. So that is the reason for which the phi itself is sometimes defined as availability. It is the index of availability. Availability. So sometimes phi, which is u plus P0 V minus T0 S, this itself is sometimes not as availability function, this is known as availability, because corresponding values with V0, P0 and U0, V0 and S0 are constant values for a given particular system of a given working substance. So therefore this is sometimes used as the availability function. Sometimes this is used as specific availability function. So specific availability function, specific, in some book specific availability, some books phi is denoted as specific availability, it does not matter, there may be many conventions, so all small, that means per unit mass. So maximum work per unit mass will be the difference of this specific availability function or specific availability. So we usually call this function itself as the availability. Clear? Concept is clear? Now availability balance of a closed system. You see how this is very, very important. Availability, please.
Sir, so to define availability, there should be some reference state with P0 and T0.
Yes, obviously. From the very beginning I told you, obviously. You have to define, because basic concept is that you have a system at certain state. Just imagine one thing. Today we have a system, closed system, whose pressure and temperature is same as that of the surrounding temperature. No process is available. So you know process is possible. So availability is 0 because you tell it is at dead state. But the same system, do you consider in the first week of January its availability was 0 at the same pressure and temperature. But that time ambient temperature was much less. You take that system to a very high altitude and the pressure is less. That means obviously, because it has to interact with the environment and come to the dead state, and during that process what is the maximum work obtainable? By its definition itself, the environment is coming. You get some heat from some temperature. If I ask you what is the maximum work we have to obtain, then you think of a Carnot's engine, Carnot's efficiency, and immediately you think of an environment temperature where heat has to be rejected, because second law tells that all heat cannot be converted into work. Otherwise the environment could not come into picture. That means you will have to think of a heat rejection concept, heat rejection temperature. And the minimum heat rejection temperature possible is the environment temperature. We cannot create a temperature below the environment out of nothing. Then we will have to create something else. We will have to run a refrigerator and all these things. So naturally possible minimum temperature is the environment temperature. That means we will have to conceive a Carnot engine working between that high temperature where from heat is coming and the environment temperature as the temperature of heat rejection. So that way in the concept, definitely environment comes into picture. This is inherent in the definition of availability. So therefore when you prescribe the availability of heat at certain temperature with reference to this environment, availability of a closed system at certain state means this state is not same as the environment state or at the dead state. So with respect to it, prescribe the environmental condition. Clear? Now which is most important is the availability balance. Availability, again exergy, all these things. This synonymous term, availability or Exergy balance in a closed system. You have to also read and think. Thermodynamics, one has to think. Only in the class, it is not like mathematics or a part of fluid mechanics where most of the mathematical equations that they are only class is sufficient, but you have to read availability and Exergy balance in a closed system. How to do it? This is very important. Now let us consider in general a closed system. Closed system. Here I consider there is a reservoir or thermal reservoir at T1. Okay, thermal reservoir at T1, from where heat is coming to the system. Let Q1 amount of heat has come. Work delivered by this system is W1. Okay, and the system, while doing so, the system property is given initial property P1, V1, T1, S1, U1, and the corresponding properties when the system comes to state 2. This is not a dead state. That means what I want to tell, that a closed system is there whose initial properties are U1, V1, T1, all are not independent, but I am showing as much as is possible. T1, S1, oh sorry, so that let us come TH. Closed system, you take heat from a thermal reservoir TH, a definite quantity of heat Q is going, don't give then 1, otherwise it is Q, and it delivers some work W, and then it comes to another equilibrium state where the corresponding properties are like this. That means I use the subscripts 2 for that state. Alright, now in doing so, we know our energy balance. What is that? Energy balance Q is equal to U2 minus U1 plus W. This is what? Energy balance, first law of thermodynamics. Now what is Exergy balance? Now Exergy balance. Exergy balance. How I will do the Exergy balance? Now you see. Now initially the availability is that initial availability, Exergy or availability balance, sometimes it is written as Exergy balance. I told you earlier they are synonymous terms, but depending upon their uses I will use the terminology conventionally. Initial availability A1 is what? Is, please tell me, U1 plus P0 T0 again, P0 V1 minus T0 S1. Okay, final availability with a scale at the dead state, U0 plus P0 V0 minus T0 S0. That is always being deducted, so that this is we use as availability. Final availability A2 is U2 plus P0 V2 minus T0 S2, initial and final availability. So therefore we write that these two are the available. Okay, now I am not writing anything. Now I find out, write the what is the net availability transferred out. Now make a balance, availability or Exergy. Now availability coming out of this system. Can you tell me what is the availability coming out of this system? There is a concept of availability transfer, like energy transfer. Is there any availability coming out of this system? Can you tell? Now A2 minus A1 is the availability of this state, but availability coming out, now you see one thing, again I am telling. Energy has got two distinct status. One is the energy in storage, which specify the state of the system, another is the energy in transit, that is work and heat, because of which the state of the system is changed, and at the same time the energy contained in the system is changed. Very careful, this is the concept. Okay. Similarly, the availability also, depending upon the state of the system and the energy stored in, there is an availability within the system, which is a composite property of the both system and the surrounding. Of course, if the surrounding, if you make fixed, universally fixed, then it is the property of the system. And another is the availability transferred, which is associated with the transfer of energy. because with the transfer of heat at some temperature T, there is an availability transfer. You understand? Similarly, with the transfer of work, there is an availability transfer. What will be that availability transfer? That will be the work itself, because work is an high grade energy. Work itself. So before doing that, I must rather say this one. I think that will be better. Before doing that, you must know this thing, that when there is a temperature T1, heat flowing Q. So energy flowing as heat is Q. So if I fix a temperature environment T0, so exergy or availability flowing associated with this energy is what? Q into 1 minus T0 by T1. That means we have to consider this. That means with this energy flowing as heat, this amount of associated availability is flowing. You understand? When you move, along with you, this much amount of mass is moving and this much amount of potential is moving, which is quantitatively defined like this. So with this flow of heat, this is the available energy. Similarly, when work is transferred, if it is transferred by a closed system because of its displacement, then the energy flowing as work, this is very important. Then the availability flowing will be W minus P0 delta V, if P0 is the surrounding. But in a control or in a control volume or an open system, when this work is developed by the shaft work, then the entire W is the availability transfer. That means the same work potential, because work is there, it is not a low grade energy. So these two concepts have to be made very clear. That means with the flow of heat energy from a temperature reservoir T1, there is then flow of exergy or associated flow of exergy with this Q, whose magnitude is this if we prescribe the environment at T0. Similarly, if there is an work transfer or work flowing, these are the energy in transit. Associated with that, the availability flow is W minus P0 delta V. In case we derive the work from a closed system where displacement work is possible, and from a control volume on an open system where the work is developed by the shaft work, then this is simply equal to W. This is a very useful relation. Then I come to here that now I can write out the availability coming out of this system is W minus P0 into let V2 minus V1. Okay? So this is the availability. Now you tell me what is availability coming in. Is there any availability coming in?
Yes.
Ability coming into the system, Is there any availability coming into the system? Yes. Now you know it very well, that is Q into 1 minus T0 by Th. Now you see, these are the two contains the availability transfer or availability flow, and these are the availability, just like this, the change in internal energy, and this is the net flow. In energy, you see the change in internal energy exactly balance the net energy out, because energy is neither created nor destroyed. But here you will see a difference. Now, if I cannot write this in the same page because the space is not there, you just follow. Now I write the A1, decrease in availability. What is decrease in availability? Decrease in availability. Decrease in availability. Please tell me. Decrease in availability, that means A1 minus A2. If I want to find out the decrease in availability, I consider there is a decrease in availability. Let me write that first. If it is not, if there is an increase, this will come negative. So if I write the decrease in availability, what will be its magnitude? U1 plus P0 V0 minus T0 S1 minus U2 plus P0 V1 plus P0 V2 minus T0 S2. Okay? So what I can write as U1 minus U2 plus P0 into V1 minus V2 minus T0 into S1 minus S2. This is the decrease in availability. Now what is the net availability transferred out? net availability transferred out. What is this? Net availability transferred out. What is this? This will be this minus this, this minus this, because this is out, this is in. So that will be P0, that will be W minus P0, V2 minus V1 plus, minus Q into 1 minus T0 by Th. Now W is what? Just see, W is Q minus U2 minus U1. So if I write this, this will be W I am just writing Q plus U1 minus U2. This I write plus P0 into V1, minus V2 minus Q, okay, plus Q into Q by Th into T0. Okay. All right. Now you see one thing, decrease in availability, and this is the availability transferred out. So if I just divide it, is availability transferred out, A out. So now if I make A1 minus A2 minus A out, what I get? 0. Should I get 0? This minus this, should I get 0? This is cancelled, but so what I get? T0 into S2 minus S1 minus Q by Th. That means this gives you the concept. Now A1 minus A2 is the decrease in availability, and this is the availability transferred out. Exactly, you are following the inertia. It should be 0 in case of energy, because what is the net out, that will cause the decrease. But here you see decrease is more than what is out of the system, because this is, what is this? Universe or sigma entropy generated, and this is the irreversibility, which is always greater than 0. That means for a natural process or irreversible process, we see that the decrease in availability is more than the availability out of the system. That means whenever an interaction is taking place, where a system changes from one state to other state with availability flow in, flow out along with the energy quantity, then though the energy quantity makes a balance like that, no energy is destroyed or created. That means the net energy flowing out must account for the energy decrease within the system, or net energy flow in accounts for the energy increase in the system. Availability does not do so. The decrease in the availability is more than the availability out. That means availability is destroyed in the system. That means if you write this, you will see that now this is the I. Now I can write A2 is A1 minus A out minus I, which is always greater than 0 by the second law of thermodynamics. That means our final availability stored in the system in its final state is less not only by the availability which has been extracted from the system plus something is destroyed. That means due to this type of availability transfer process associated with the transfer of energy, some availability is destroyed because of the irreversibility. If the process is reversible, then this is 0. Then availability at the final state is the availability of the initial state minus the availability, net availability out of the system, which is synonymous to the energy balance equation. So therefore we see in this process also availability is destroyed. The way we saw that heat is destroyed, that availability with respect to heat energy is destroyed when we make a natural heat transfer process from a higher temperature to lower temperature. Similarly, in a natural process executed by a closed system, through the interactions of heat and work with the surroundings, the availability is destroyed. That means we destroy the availability. This availability is what? Work potential of the energy, and this is defined as the quality of energy. So therefore we can say that quality of energy is destroyed in all natural processes. Therefore you see, in all natural processes entropy of the universe is generated, while the quality of the energy contained in the universe is being degraded. That means is reduced. That is what is known as law of degradation of energy. A very simple example with IITians, that when you come to the IIT, your quality is at some value which is being degraded throughout the 4 years. Teachers are not responsible for that, you yourself are responsible for that. For the natural processes you incur, you degrade, because the work potential of a person just after JE is much more than the person who goes out of IIT, but teachers are not responsible.